Hello everyone. Today we are going to talk about normal probability. Now this is the basic for using statistics into research purposes. Whenever we do researches in a quantitative methods, we collect a large amount of data. But how to analyze or how to put the data in the tabulated form so that we can find their normal distribution and the standard score that shows the differences, and how to find the mean, the variations can be known from the normal probability. Normal probability is also called as Gaussian distribution. It has been named after Carl Friedrich Gauss, who has given most of its properties. Now, when we get a large amount of data, we have to arrange the data in such a way that the data, when presented graphically, shows bilaterally symmetrical bell-shaped curve, whereby the data is evenly distributed, and this distribution of the data shows that the data collection has been done in the normal tendencies, whereby majority of the data will fall towards the middle of area around the mean, and the least of the data will fall on either side of the graph. So, here normal probability shows the distribution of the sample collected for the data analysis. The normal law of probability curve is based upon the law of chance of events. In common terms, probability means uncertainty, but in research and statistical term, probability is defined as the expected relative frequency of a particular outcome. So, we judge the normal probability by the expected outcome and the total number of outcomes that can possibly occur. Knowledge of probability theory makes it possible for the statisticians and the researchers to find out the tendency of the population and their interests, likes, dislikes on whatever research topic that we are doing the study upon. Basically, the probability of a given expression of likelihood of occurrence ranges from 0 to 1, whereby 0 denotes that the likelihood of occurrence is not going to occur, whereby 1 denotes that the likelihood of occurrence is definitely happening. As we can see from the slide, the probability of an unbiased coin falling heads is 1 by 2, and the probability of a dice showing a 2 spot is 1 by 6. So, from this probability we can find out how many chances are there for the dice to be falling 2 and for the coin to be falling head or tail. The definition of probability given by Laplace is as shown in the slide. If probability is denoted by P, then by this definition we have P is equal to desired outcome by total number of outcomes, which is expressed as a ratio. The probability of H is 1 by 2 and of T by half. Now, we shall see the most important properties of normal distributions. As we can look into the slide, the normal probability curve is symmetrical above the mean. The skewness here is 0. For example, if the curve is divided by a line drawn perpendicular through the center, then the high point to the baseline, there will be 2 equal halves in all respect. Here we can see the properties such as 2 parameters m and standard deviation determine the location and shape of the distribution, where m is the mean and standard deviation is denoted by the symbol presented in the slide. The height of the normal curve is at its maximum at the mean. The normal distribution values of mean, median and mode are equal. The standard deviation determines the width of the curve. Larger values result in wider, flatter curves. The curve asymptotic to the base on either side. That means the curve approaches nearer and nearer to the base, but it never touches the base. Since there is only one maximum point, the normal curve is unimodal. That means it has only one mode. Now, when we see the normal probability graph, we can see the distribution of the data in the following way as shown in the slide. The area under the normal curve is distributed as follows. 68.26% of values of normal random variables are within plus or minus 1 standard deviation from the mean. That is 34.13% area lies on either side of the mean. Then 95.44% of values of a normal random variable are within plus or minus 2 standard deviations from the mean. 99.72% of values of a normal random variable are within plus or minus 3 standard deviation from the mean. Then, which indicates 95% of values fall between plus 1.96 to minus 1.96 standard deviations from the mean, and 99% of the values fall between plus 2.58 to minus 2.58 standard deviation from the mean. A random variable that has a normal distribution with a mean of 0 and a standard deviation of 1 is said to have standard normal probability distribution, and it is designated by the letter Z. The normal curve is always continuous. When the data has been distributed on the graph and we have found that the sample is normally distributed, then we interpret the data as in the following way. We can see it from the slide. A normal probability distribution table is useful when the scores are normally or near normally distributed. The values given in the normal probability table are critical, which provide data for normal distribution. That may be interpreted by converting the score into Z standard scores. A Z-score indicates how many standard deviations the corresponding raw score requires to lie above or below the mean of the distribution. This statement is been put into the form of formula that we can see as Z is equal to x minus m by SD, where x is equal to given raw score, m is equal to the mean, and SD is equal to standard deviation. Now, when we use the formula, how we apply the formula and what are the uses of the formula, let us see it from the slide. The applications. Here the normal probability distribution help whether the distribution is normal or not and how much it diverges from the normal. To calculate the percentile rank of score in normal distribution. It helps in understanding the concept of standard error of measurement, and it helps in comparing scores on distribution where total numbers may differ. A sigma score Z allows for comparison of scores from data that have different means and standard deviation and gives the exact location of any score in a distribution in relation to the mean. Now, we will incorporate the formula into some examples and we will see, as it is presented in the slide, converting the raw scores into comparable standard scores, that is Z scores, and vice versa. So, in the first condition where we are finding the raw scores and the Z score, here we have, for example, m is equal to 60, that is mean is equal to 60, SD is equal to 10, that is standard deviation is equal to 10, and we have to change the score of 80 into Z score. So, we incorporate the data given to us into the formula as follows: Z is equal to 80 minus 60 by 10, which gives 20 by 10, and we get the Z score as 2. Now, in the second condition where Z score has to be converted into the raw score, here we have been given the mean of 40, the standard deviation of 6, and we have to convert a Z score of value 0.5 into a raw score. So, incorporating the information given to us into the formula, we get 0.5 is equal to x minus 40 by 6, which gives us 0.5 into 6 plus 40, and the raw score that we require is 43. Further, we can incorporate the formula into the following problem. As we can see from the slide, a student secured 75 marks in physics and 55 marks in chemistry. The mean and ST for the score in physics are 50 and 25 respectively, and for chemistry the scores are 25 and 10 respectively. In which subject the performance was better, we have to determine. Now, we put the information and then we put the information into the formula. For physics, raw score, that is x, is 75, mean is 50 and SD is 25. Chemistry, raw score, that is x, is 55, mean is 25 and standard deviation is 10. We have derived it from the question itself. Then we incorporate the scores into the Z formula. So, the Z score for physics is equal to 75 minus 50 by 25, which gives 25 by 25, and we get a Z score of 1. Similarly, Z score for chemistry is 55 minus 25 by 10, which further gives us 30 by 10, and we get a Z score of 3. On the basis of the Z score, it is clearly evident the performance was better in chemistry than physics. Then we see how the Z score even helps us finding percentages of scores, which can be determined by the following sample. In a sample of 1000 cases, the mean of test score is 12 and standard deviation is 2. In normal distribution, how many individuals has scored between 10 and 15? both the raw score 10 and 15 have to be converted into z-scores first. So, we can see from the formula z is equal to x minus m by standard deviation, that implies to 10 minus 12 by 2, which further implies to minus 2 by 2, and it further shows minus 1 standard deviation. Then similarly, we can see 15 minus 12 by 2 is equal to 3 by 2, which gives us 1.5. From the normal curve table, we see that 4332, that is 4332 out of 10,000, that is 43.32% cases, that is between mean and 1.5 standard deviation. Similarly, between minus 1 standard deviation and mean, 3413, that is 34.13% of the cases lie. In this way, it may be easily concluded that 43.3 plus 34.1 is equal to 77.4% or 774 individuals out of 1000 scores between 10 and 15. We can see further in the next example of a problem whereby in a sample of 300 cases, the mean is 25 and SD is 2. Taking into account the normality of distribution, find out how many individuals score above 28 score point. So, here the z-score is equivalent to the raw score 28 is given by the formula x minus m divided by standard score, which is implied as 28 minus 25 by 2, that is 3 by 2, and we get 1.5 as standard deviation. From the table, it may be found that 4332 out of 10,000 or 43.32% cases lie between the mean and 1.5 standard. It is also a fact that the total of 50% cases lie on each side of the mean. Therefore, it may be concluded that in all 50 minus 43.32, we get 6.68 or 7% individuals or 21 individuals out of 300 scores above the score point of 28. Then we look at the types of curves, normal probability curves that we can have and the deflections in them. In one of the forms of curve we have is called as skewness. Now, when the data is distributed on the graph and it is not being centralized in the middle, is near to the mean, then it is skewed. It is not symmetrical. This indicates that the data or the sample that has been collected is not normally distributed. This skewness can be presented in two ways: positive skewness and negative skewness. In positive skewness, the right side of the tail of the graph is longer and the majority of the mass of the data lies on the left side of the graph, and the mean is higher than the median, whereby in normal distribution all mean median mode are equal. The distribution here, when it is skewed towards the left side, the majority of the result is on the left side, is called as skewed to the right, whereby the right side tail is thinner. On the other side, we have negative skewness, whereby the left side of the graph, the tail is thinner and the majority of the mass of the data collection is on the right side. Here, the median is greater than the mean, and this distribution of the data is called as negatively skewed, as we can see from the slide. Now, further seeing from the slide, we can see skewness in a given distribution can be computed by the following formula. That is, skewness is equal to 3 into mean minus median by standard deviation. When percentiles are known, the value of skewness may be computed by using the formula Sk is equal to P90 plus P10 by 2 minus P50. Further, we have another form of graphical representation of the data that may not be symmetrical, and that form is called as kurtosis. Kurtosis is the degree of peakedness of the distribution. In Greek, it means bulginess. Either it is peaked, the data that has been collected, or flat relative to the normal distribution. Now, we have here 3 types of kurtosis that shows the distribution is deviating from the normalcy. The first one is called as mesokurtic, as we can see from the slide in the form of graphical representation, whereby mesokurtic is the normal curve and it means intermediate peakedness. Platykurtic, the data has a flatter peak around its mean, which causes thin tails within the distribution. The flatness results from the data being less concentrated around its mean due to large variation within the observation. Leptokurtic is the form of kurtosis whereby distribution have higher peaks around the mean compared to the normal distribution, which leads to thick tails on both sides. These peak results from the data being highly concentrated around its mean due to lower variation within the observation. Now, further, the value of kurtosis can also be determined by the following formula. Ku is equal to quartile deviation by 90th percentile minus 10th percentile. These formulas of skewness and kurtosis help us to determine whether our data collection has been normal or not. It has to be around the normalcy for applying further statistical method and interpreting the results. If the data is highly skewed or highly kurtosis, then it will lead to error in our analysis of the data. So, these are some of the basic guidelines that all the students and the research people need to know before doing the data interpretation.